Hey everybody, another exciting time of trigonometry. Actually, the very last section that we are going to cover before we move into our actual calculus and all that entails. So, what we're going to work on today is section 12.6 from our book, and that is talking about polar equations. So the first thing we're going to look at doing tonight is we are going to graph polar equations. And probably, just like when we started graphing lines and things like that way back in the day, we're just going to start by plotting some points, plugging in some values for theta, and then figuring out what the corresponding r is going to be. So we'll use this equation here, r equals 4 sine theta. And we'll make a nice little chart like you did back with your XY table, things like that, way back a long time ago when you were in your first year algebra, things like that. And we'll plug in some different values for theta. So we plug in 0, and the sine of 0 is 0, times 4 is still 0. And we'll plug in some other pretty easy to remember angles. That should really be pi over 4. So plug in the sine of pi over 4, and sine of pi over 4 is, 1/2? And not pi over 4, but pi over 6 is what that should be. Pi over 6. So sine of pi over 6 is 1/2, times 4 is 2. Sine of pi over 3 is radical 3 over 2, times 2 is 2 radical 3. Sine of pi over 2 is 1, times 4 is 4. And we'll go all the way until we get to 2 pi. Okay, and you can do that if you like. You can push pause right now and continue to plot those points if you want. Now we're going to graph that, and we start graphing that on our polar graph. Remember that we always have an r, we always have a theta. Theta tells us the direction, r tells us how far to go. And so I'm just kind of sketching it, half-heartedly, I guess, if you will. And I can see from all of these points here that eventually I am going to get a pretty sweet circle right there. That circle whose center is 0, 2. Or, if you will, that would be what in polar coordinates? Like a 2, pi over 2, with a radius of 2. And so that's one way that you can graph. But you can also do a lot of graphing and maybe save you a lot of time by thinking about symmetry. And so there's 3 tests when you're graphing polar functions, or polar equations, I guess is what you should say, that will help you know if the graph is going to be symmetric. 3 tests. And again, what is it that is important about knowing this? Why do you want to know if you have symmetry for it? I don't know if you've answered that question to yourself at all, but the answer to that is fewer points to plug in. You don't have to graph all the way up to 2 pi if you know that it has symmetry in one particular direction. So the first test, if you can replace r, theta by the opposite of r and the opposite of theta, and you get the same answer, or if you can replace it by r, pi minus theta, so like the supplement of that angle. If you get the same answer, then you know that you have vertical symmetry. At any point you want to pause this and think about why that is. Think about why you have that symmetry. Do that. Try to work on understanding why it has symmetry in one particular direction. The second test is if you take r, theta, so that would be any of those points you have up there above in that chart, and you replace them by r negative theta, or if you replace it by the opposite of r, pi minus theta, the supplement again, and you get the same answer there, then you have horizontal symmetry. So again, feel free to pause and really try to understand why that is. Why do you have symmetry in those directions in this case? And then the third one, if you replace r, theta by r, pi plus theta. So what we're really saying is if you go 180 degrees away from where you're at right now, and that result gives you the same point, Or if you just go the opposite direction, so the opposite of r comma theta, and you get the same result, then you have what's referred to as polar symmetry, or symmetry. Basically, it's like 180 degree symmetry. It's diagonal symmetry. It's symmetry across the origin or the pole. So as we go through the examples the rest of this video session, I want you to think about which of the examples have these kinds of symmetry. I might not talk about it very much. I'm really asking you to really be observant right now. Again, pushing pause, thinking about these ideas, and coming up with whatever you find out with that. So the first thing we're going to do right now is we're going to try to sketch a graph. And that graph is going to be r equals 3 plus 2 cosine of theta. Now, we can replace r comma theta with r opposite of theta. Now again, why do I know that? How do I know that I can replace that in this problem? I bet you that there's a lot of you that have no idea why that is. If you want to push pause and think about how I know that better than you right now, do that. And so since I know I can do that, then I know that this graph is going to be symmetric horizontally. Alright, symmetric across the the horizontal axis, what we would normally think about as the x-axis on a regular graph. And so that means that I don't have to plot 0 through 2 pi or 0 through 360. Since the bottom of the graph looks exactly like the top, I only have to plot 0 through 180. So again, knowing what that symmetry is can save you a lot of time in plotting points. Now, if you haven't figured out how I knew all of that yet, I know that because I know that cosine is an even function. So I know that when I plug in theta or I plug in the opposite of theta, I'm going to get the exact same answer either way. So yeah, now I'm going back and pulling those old ideas from earlier in the semester, odd and even functions and things like that. So a lot of this really, ties together. Alright, so if I just plug in those points from 0 to pi, alright, and you can do that yourself. You can plug in some of those values and figure out where they're going to be, where your corresponding r value is going to be. You'll get the following graph. Again, I'd really recommend that you try it first. Again, those are values that I've plugged in on my own. And those are kind of sketches again, but you get the idea. And remember, the bottom of this graph is going to look exactly like the top. It's going to be symmetric, so I can go ahead and draw the mirror image of that, and it looks something like that. Almost like a, I don't know, like a bean, something like that. I don't know. So I'd like you to try these two examples now without me having you go through it. Remember, you can put these into your calculator, but it sure would not hurt to try them by hand first, especially as you consider the ideas of symmetry with them. See if you can actually graph a lot of this graph without having to plot the whole entire 0 through 2 pi. Alright, so try graphing r equals 1 minus 2 cosine theta, and then r equals 3 cosine 2 theta. You notice I've changed the period of that second one. Think about what that might do to the values you need to plug in. So again, I'm leaving you a reminder to look for symmetry in these problems. Look to see if you can save yourself some time and effort. If you're having a really hard time plotting points here, don't just give up and rely on the calculator. Remember, your calculator You got to be very careful with that. At times, if you don't set your window settings up just correct for that, you can really misinterpret what the graph is supposed to look like. So please make sure that you understand this. Take some time with that, even though it might not be very exciting, and you might think that there's way better ways to do it than plotting thetas and finding their corresponding r's. I really think that this is an idea that you want to have in hand before you get to the next quiz. So our last idea we're going to work on tonight is understanding some special kinds of polar graphs. There are, I think we talked about in class earlier that there are some really cool looking graphs that you can make with a polar graph. Some cool designs that, well, quite frankly, you can't do on a XY coordinate plane, a Cartesian coordinate plane, very easily at least. All right, so there's a couple different families here. I'm gonna write down each of those families, tell you what the forms of the equations look like so that you can recognize them when you see the equation, and then show you a little picture of each of these families. You are going to have to be able to identify these types of graphs on a quiz, either by looking at the equation or by looking at the graph. Know what family, what kind of graph you're looking at. The first one is referred to as a lemicon. Lemicon, it's pronounced lemicon. That I has got like an E sound to it. Now, a lemicon is going to be identified when it's in this form. When you have r equals a number, a constant, plus or minus something times in cosine or sine. Right? Don't really worry about the a and the b greater than 0. It's not super important. Just remember it's of this form. Okay, and the a and the b could be 0, a could be 0, or b could be 1, something like that. Now, if you have this form, you're going to get one of the following pictures. You either are going to get a little swirly graph like that, or you're going to get one that comes to a point like that, or you'll get one that's similar to the one that we had just a second ago. If you notice, that was of this form, kind of like that bean thing. Alright. Now, that middle one, since it kind of looks like a heart a little bit, has a special name. It's referred to as a cardioid. And for those of you that know medical terminology, if you have cardiac arrest or a cardiologist, those are things that have to do with the heart. So that's a way you can remember that. Each of these, though, is in the lemicon family. The next family of curves are referred to as rose curves. Rose curves are of this form. So you don't have that constant out in front, but you have a number multiplying either cosine or sine, and then sometimes you'll have a different period put in there with your theta. If that period's an even number, then you are going to have 2 times that number of petals. If it's an odd number, then you'll have just that number of petals. And the petals look something like this. So there's an odd number of petals. Some people think it looks like propellers from a plane. But that's the idea. So those are rose curves. And then the last family are referred to as lemniscates. Lemniscates. And the easiest way to recognize those is there's a lot of squares in the problem. So r squared equals a squared sine 2 theta, or cosine of that. Pretty specific. And it sounds like it should be a really funky graph, but basically it's just like a bow tie. You'll either have one that's horizontal, or you'll have one on the diagonal. So these are all different families that kind of are special graphs, cool looking graphs, ones I want you to be familiar with. If you want to look in your book on page 790, it has all this information there as well, with maybe a little more additional information to help explain it a little bit better and give you a little better insight with these. So your homework assignment is going to be on page 791. I'd like you to do problems 1 through 12 all. Again, that's just going to be you identifying some things on the graph. And then try to do 23 through 47 odd. And again, you'll be tempted just to use your graphing calculator on a lot of this, just to graph them and see what they look like. But I would really recommend that you do more than that. Have a good time. We'll see you next time.